Okay, dear students, welcome to this video. In this video, we are going to learn about the application of the Fourier's law that we just did. So the first application is that let us consider a wall here. So this wall is separating two different chambers. So you can say this room here, it is maintained at a higher temperature, which is T1. In this case, you can call it TH, no problem with that. And the room on this side, on the right hand side, is maintained at a lower temperature, which is TC. Now you can just imagine as if you are sitting in your room and inside temperature is different and outside that there is cold climate there, let's say, and the temperature is different. So these are two different temperatures that we are maintaining, and obviously heat loss will be there. Yes, we use the non-conducting materials to create our walls these days, that is separate case, but still some energy is definitely going to flow. There is like there are bad conductors of heat, but it's not that heat will not be conducted. Okay, so very less amount of heat can be conducted from the bad insulators, but from the bad conductors, but there will be some heat. So here also we are giving some heat out. So this temperature is T1, which is maintained here, and this temperature maintained is T2. And this line which is shown here, which is actually like you need not to know about it, but still this is actually the temperature profile within the wall. So within the wall it is a linear variation for the temperature and the distance. So clearly the temperature is falling like this. So this is how the temperature falls. So you can even find the temperature gradient that we usually do in higher engineering courses and others. So even now you can do it, it's not that very big deal. Okay, so let us now apply the Fourier's law to this. So according to the Fourier law, the rate at which heat will be flowing, so this is the rate at which the heat is lost from your room to the environment, that is delta Q by delta T is equal to Ka divided by L into delta T. So let me tell you, delta T is Th minus Tc, and L is actually the length of the wall, the thickness of the wall. Sometimes it is also written as delta X. So it is written like this. If you want to find the gradient, that is the slope of this line, if you want, you would be using delta T by delta X. Now delta Q by delta T is a linear variation. It is a constant value. It is not changing. So this is a constant, K is constant, A is constant. From there, we can very easily understand that the gradient, which is delta T by delta X, will come out to be a constant value. It means that the slope is not changing. That is why we are having a linear variation of this temperature gradient. So this is starting with the higher temperature Th, it is going towards a Tc with a constant slope with a straight line variation. This is what is happening inside the wall. Okay, coming back to the Fourier law, so delta T by delta X. So what happens is that in this case, we are going to compare it with electricity. That is the topic B5. Okay, so we would be doing the topic later, but I assume that you know a bit of it, like V is equal to IR, which is Ohm's law. So this is very easy, isn't it? V is equal to IR. So I would be using those formulas for series as well as parallel and all that. We would be understanding that. So if you have yet not done B5, so you can be careful here. If you have already, you have an idea about series combination and parallel combination for the resistances and others to a very basic level, then you can continue with this. Okay, so this is the gradient, which is this. So what happens is I am going to compare this thing like delta Q by delta T is equal to delta capital T divided by this. So instead of delta X, now I am interested in writing it as L, and Ka goes to the denominator further. This becomes this. So delta Q by delta T is the rate at which the heat is going, but I am going to compare it with electric current, the rate at which the charge is flowing, something like that. I'm just comparing. This is called electrical analogy. It's very important, students, so be very careful. Electrical analogy. So this I'm calling it as the current which is moving through the wall or which is moving through the rod. Delta T can be compared with the potential difference. Okay, and L by Ka is resistance. So there you are, V is equal to IR. This is the Ohm's law, and this is the Ohm's law for thermal engineering, for the heat transfer. So now we are comparing. Obviously, in the wire, the electric current will be flowing if the potential difference is there. If potential difference is not there, the current is not going to flow. Similarly, heat is not going to flow through the wall if the temperature difference is not there. So temperature difference has to be there. So it is delta V by R. Clearly, I can say that the thermal resistance will be given by L divided by Ka. That is the thermal resistance, L divided by Ka. So, by thermal resistance, what do we mean? It is the resistance provided by the conductor to the heat flow which is trying to pass through it. Clearly, we can say that the resistance is directly proportional to L, which is the length of the rod. Even in the case of electricity, resistance is directly proportional to the length of the wire. More is the wire, more is the resistance. Similarly, more is the area. So bigger the wall, the area is bigger, then the heat flow will be easier. So it means that the resistance will be lesser. The resistance is inversely proportional to the cross-sectional area of the wall. Similarly, K is the thermal conductivity. So more is the thermal conductivity, better is the conductor, and lower will be the resistance. So even the thermal conductivity is inversely proportional to the resistance. From here, I can even tell you that in the case of current and electricity, we are going to do it in the topic B5 in details. Resistance is given by resistivity into L by A, or it is also given by 1 by K, which is taken as conductivity in that case, L by A, which is very similar to the thermal resistance. Here, this rho is resistivity, and the K is conductivity, which is actually the inverse of the resistivity. So they are completely analogous to each other. That is why this is known as electrical analogy of the Fourier law or the walls thing. So this is it for the electrical analogy for the wall. But what about the composite walls now? Okay, let's see. So this is another case now. This is the case of composite walls. Now, the thing with your syllabus is that they have not given the composite walls explicitly. They have not mentioned that in your syllabus. But IB is always unpredictable with some what kind of questions they're going to ask you in paper two and something. So if they have brought in the concept of thermal resistance, they have brought in the concept of Fourier law, definitely you must be like you must ready yourself for the surprises that you're going to get in this. So this is a very small topic, that is why I decided not to skip it. So I would be telling you this. So composite wall is like, let's say there are two different walls which are there. So first the temperature is falling like this to some intermediate temperature, then it is further falling to T2. So what we do in these kind of cases, it's a very simple process, and this is known as series combination of the wall. So we are not going to think from the thermal conductivity point of view, but we are going to consider the electrical conductivity point of view. So the resistance first will be L1 divided by K1, and area is taken to be the same. In both of the cases it is A, and the second resistance will be L2 divided by K2 into A. So we are going to find the total resistance here. In series, we know, and if we do not know, you would be going to learn it in B5. R is equal to R1 plus R2, which is coming out to be 1 by A, L1 by K1 plus L2 by K2. Okay, that is the thermal resistance R. So R is this, and accordingly we can find the total resistance. So the total current which is flowing through it, or the total heat which is flowing through the wall, that will be equal to the total potential difference or the total temperature difference across the wall, which is T1 here and T2 here, which is T1 minus T2, higher minus lower, divided by the resistance which we just found. Accordingly, we can find the value of delta Q by delta T. So this is kind of the highest level at which IB can ask you questions, okay, from this topic. So no need to go beyond it. Like, even this is like more than enough for you. So this is series combination. We would be going for the parallel combination also. So let us move to the next slides. Yeah, here. So this is a parallel combination, and we can just believe there are two different walls but the rooms are the same. So clearly it is compared with two resistances which are placed in parallel like this. So nothing to worry about. We will find the first resistance as L1 divided by K1A. And in this case, even the area is different, but L is the same. So we are taking it as L, but the area will become A1 and the resistance 2 will become L divided by K2A2. I I would like to recall that the thermal resistance, we had a general formulation L divided by Ka. I'm using that only. So I converted this thermal system into electrical system, which is very easy to deal with. So R1 R2, and now we know how to find the parallel resistance. 1 by R is equal to 1 by R1 plus 1 by R2, and accordingly you can find the composite resistance of the wall, and then we can just find the current, which is delta Q by delta T, is equal to the total change in temperature divided by the composite resistance. This is it, the application of the Fourier's law to the wall, and we have done the combination of the wall series as well as parallel, and the conduction topic is completely over. We need not to move further, we need not to go further, you need not to do anything other than this is enough. Okay, dear students, and you already know the profile also. We already had a discussion about it, that this profile here is going to be a linear line, a straight line which is joining T1 with T2, and so you can create a graph out of it. Like this could be the temperature and this could be the thickness. So let's say this is the wall that we are considering, and so this is T1 and this value is T2 here. So the profile will be a straight line between T1 and T2. So this kind of graphs can also be asked. So this is very easy, I believe. So you can just do it, just understand it, and if there is any other problem that you face, just mention that in the comment section. So dear students, conduction is over. All the best. Bye.